Hi, we are starting Chapter 4, the atomic structure. And this first lecture is actually going to be over 4.1 and 4.2 in the textbook, starting on page 100 through 108. As always, you should kind of be reading the chapters as we go and looking at the review questions at the end of each section. There's a set of review questions on page 103 and also on 108. At the beginning of Chapter 4, it's going to talk about the early models of the atom and some of the early scientists and some of their ideas about matter. Democritus was one of the first guys to mention atoms. He said the world was made up of empty space and atoms. Aristotle said matter was continuous. And then came Dalton, and from there we got the Dalton's atomic theory, or the atomic theory of matter. And in the book there's 4 parts to that, and I've kind of summarized them here. Atoms can't be created nor destroyed. They can only be separated, joined, or rearranged. All elements are composed of atoms. Atoms can be broken into smaller particles like the electron, the proton, and the neutron. And you can see there how I abbreviated electron, proton, and neutron. So if you have an atom and you break it down smaller, you don't have that atom anymore. You have the parts to the atom. So if we have an oxygen atom, I have oxygen. But if I break that down, I just have the electrons of oxygen, the protons of oxygen, and the neutrons of oxygen. I don't necessarily have oxygen anymore. All atoms of an element are exactly alike, but different from other elements. So atoms of one element are all the same, but they're different, I should say, from other elements. Atoms can combine in ratios that we called compounds that have the same relative number and kinds of atoms. And we learned in the last chapter that if you say have H2O, we cannot change the composition of that. If we do, we don't have H2O anymore. We don't have water. Then there was a guy called Avogadro, and he said equal volumes of gases under the same conditions will have the same number of molecules. It doesn't matter what the gas is. If you have the equal volume of gas and it's put under the same conditions, meaning like temperature and pressure, you're going to have the same number of molecules. There was a guy named Millikan, and he was the first one to accurately measure the electron charge, so the charge of an electron. Millikan worked with Thomson, and they found the mass of an electron, 9.11 times 10 to the negative 28 grams. Very, very small mass there. And Thomson did his famous cathode ray experiment, and from his experiment they found out that atoms contain electrons. So his experiment, they found that atoms had electrons, and then Millikan did his experiment and found the charge of the electron, and then Millikan and Thomson worked together and got the mass of that electron. So with Thomson, what he did, he sealed gas in a glass tube and fitted both ends with metal discs called electrodes. The electrodes were connected to a source of electricity. One electrode, the anode, became positively charged. The other electrode, the cathode, became negatively charged. The result was a glowing beam, or a cathode ray, that traveled from the cathode to the anode. A cathode ray is also deflected by electrically charged metal plates. A positively charged plate attracts the cathode ray, while a negatively charged plate repels it. Thomson knew that opposite charges attract and like charges repel. So he hypothesized that a cathode ray is a stream of tiny negative charged particles moving at high speed. Thomson called these particles corpuscles. Later, they were named electrons. Okay, so electrons. And when you're talking about a cathode ray, there's the anode end, which is positive, the cathode end, which is negative. And the ray starts at the cathode end and travels to the anode end. Then there's Madame Curie. Her and her husband had done all kinds of experiments, and they found that rays are given off by certain elements, and they worked specifically with uranium and radium, and those are called radioactive rays. And she actually died at a very young age due to cancer because of her work with these elements. And then, of course, there's Einstein. He said mass and energy are equivalent, and that's where he came up with his famous equation, E equals mc squared. Then there's a guy by the name of Goldstein, and he said atoms have a positively charged particles, and they were called the protons. So his experiments led to them to know that there was protons in our atom. Chadwick confirmed that atoms have neutrons. Neutrons have no charge, and their mass is equal to a proton. And then there was Rutherford. He did his famous gold foil experiment, and they found that the atom is mainly empty space, but there is a center part that holds the protons and neutrons, and they call that center part the nucleus. And the empty space is where all these electrons are. And on page 107 in the book, it talks about Rutherford's gold foil experiment, and I'll read just a little bit to you. A narrow beam of alpha particles was directed at a very thin sheet of gold foil. According to the prevailing theory, the alpha particles should have passed easily through the gold with only a slight deflection due to the positive charge thought to be spread out through the gold atoms. They thought that the protons and electrons were spread evenly throughout the atom. Kind of like if you look at a chocolate chip and you have chocolate chips spread out evenly. To everyone's surprise, the great majority of alpha particles passed straight through the gold atoms without deflection. Even more surprisingly, a small fraction of the alpha particles bounced off the gold foil at very large angles. Some even bounced straight back toward the source. Based on his experimental results, Rutherford suggested a new theory of the way the atom looked. He proposed that the atom is mostly empty space, thus explaining the lack of deflection of most of the alpha particles. He concluded that all the positive charge and almost all the mass are concentrated in a small region that has enough positive charge to account for the great deflection of some of the alpha particles. He called this region the nucleus. The nucleus is the tiny central core of an atom, and it holds the protons and the neutrons. Then there was a guy called Proust, and he came up with the law of constant composition, and that is just that compounds always contain the same elements at the same proportion. We've talked about this over and over. The composition of compounds can't change. Proust came up with this, and it's known as the law of constant compositions. Rutherford then worked with Bohr, and they determined that electrons are in orbit around the nucleus as the Earth is in orbit around the Sun. And that model held for a very, very long time. But now the latest model is known as the electron cloud model, and these electrons are in orbit around the nucleus at various energy levels. It's not really like they orbit like the Earth is around the Sun, because they can bounce from energy level to energy level as needed. And the main ones that are bouncing are the outer shell electrons, or those outer electrons. Those are the ones that get stimulated, and they can move to higher energy levels or to lower energy levels. And that is the end of the first lecture.